Swayam Prabha. Digital India. Educated India.
Good. So, good morning. So, myself, Muhyuddin, I am a synthetic organic chemist and or stereoselective Aldol reaction. So, let me begin with the so in the if as you know, this is a very old reaction and most of you are quite familiar with that. So, we will start with the beginning and then slowly we will move for the advanced one. So, what happened in the Aldol reaction? You guys, if you remember. So, you have an aldehyde and then that reacts with an carbonyl compound has an alpha hydrogen. Okay, so let's say I am putting R1 and R2, and that goes in presence of a base, and you make a compound like a beta hydroxy carbonyl compound. R1 and R2. Okay, this is the classical reactions or is a general reaction scheme, and you will see most of the books is mentioned like that. What exactly happened here? So, your base job is to deprotonate one of the alpha hydrogen from this carbonyl. So, what is exactly happening that initially you generate an enolate from this one. So, you generate an carbon ion here, and that carbon ion is reacting from this way. Okay, that is the thing. Now, when you generate the carbon ion, and because it is an unsymmetrical, so you would lead to a two scenario. One case is that you get a, let's say, O minus and the R1, and these R2 like that, and there is one hydrogen. This is one scenario, and one more scenario would be also that you could have O minus R1. Now R2 is here and hydrogen is here. So, what you exactly get here in this case, your O minus and R2, those who are priority higher in both the carbon are in opposite to each other. So, you generate an E enolate. So, this is an E enolate. On the other hand, you can have then R2 and O minus are in the same side of the double bond. So, you are actually making this double bond is a cis double bond, or we can say a Z enolate. Okay. So, this two scenario is possible in presence of a base. Now, once this enolate generate, it's now can react with the aldehyde coupling partner. So, this can come back and then this react with the carbonyl center, or similarly this can come back and that goes to the carbonyl reaction. Now, this would lead to two different scenario. So, from the E enolate you get a one kind of product, and with the Z enolate you get another kind of product. So, from the E enolate, what product usually we get? So, you get, so you can have a this one or the mirror image of this one, because right now it is a racemic reaction, or the mirror image of this one. That means you get this one. Okay. Both of them is going to be formed because it is a racemic form now. So this is for the E inolet. So E inolet will give you this compound, and you can see that here OH and R2 are the opposite side. In this case also OH and R2 opposite side. So we call it an anti-product. Okay. Or we can say it's an anti-selective. Now, if you start with the Z inolet, you get the other one, that you get a either this and its mirror image. We are designating as R1 this one, this is R2. Okay. Now, these two bond OH and R2, they are cis or syn to each other. These also syn to each other. So, it is a we can see the syn selectivity. So, this is the basic way to figure it out. Now, one thing is very clear is if you have the E inolet, you can get the anti, and if you get Z, you get a syn. To get a one of the selectivity, we have to figure it out. How do we get an exclusively E inolet as well as the exclusively at the Z inolet? Because if you get a mixture of these two in the process, you actually get a mixture of both the product, syn product as well as anti product. But if you can have an exclusively E, you can get a anti. If you can have exclusively a Z inolet, you can get the C. So now our job is now to figure it out. How do we make this inolet exclusively for this reaction? Because this is the key. Once we have that, then we can predict what is going to be happen, and we will see how this product or this inolet is leading to the syn product and this inolet leading to the anti product. So let's have a look how we can figure it out. So base, one of the standard base which we are going to use for right now is LDA. So all of we know lithium diisopropyl amide. This LDA base usually we are going to use, and typical reaction condition usually we have an very anhydrous solvent like a THF, and goes to the low temperature of minus 78 degrees centigrade. So if I just try to rationalize at the beginning that what we are going to now look at it, let's take an example of we have, let's say simple R, and we have a methyl here, and at this condition we are adding the LDA, and that is in THF solvent at minus 78 degrees centigrade, and we are planning in the process that in one cases O minus lithium plus, and in this case we will get so this is, I can say, is an E inolet and this is, I can say, Z knowledge. Okay. Now, how this is going to happen? So, let's see how the LDA is reacting with the with your carbonyl compound. So, I am just drawing the transition state. What is exactly happen in this particular case? So, what I have drawn, can you see this ketone? So, R, CO, CH2 methyl, and this is the LDA. So, initially they have a coordination to the oxygen, and this minus, this is the base, will pick up this proton. This is one scenario. You can take that, the another one, for example, we can draw the down that. So, you can have a carbonyl lithium and now I take the methyl up and then hydrogen here. This is the scenario. So, what is the difference is that in this case this R group and the methyl group are in the same side, and in this case the R group and methyl group in the opposite side. Now, the question is which one is going to form? Because if you look that from here, if you deprotonate, what is exactly going to be happen? This bond will be formed and this pi bond is going to break. If that is happen from this intermediate, you actually get R and methyl would be in the same site. That means the methyl here and R here, and the other side you get O minus, and there is an hydrogen. Okay, you guys can see from that side. Why you don't come this side actually? Because it's spreading a little bit problem. If you because that is if you are not difficult to see, just see the other portion actually. If you are comfortable, that is fine. On the other hand, if you take that one, so you can have a this protonation, and in this position you can see your R and methyl in the opposite side, or other way this O minus whatever is going to be formed and the methyl would be in the same side. So, that means you will have a R and O minus methyl and the hydrogen. So, if you look at that, this is my E enolate and this is my Z enolate. Okay. Now, the question is which one is going to be formed? That depends on the nature of R. Okay. Think about that. If R is very big, so you induce an steric interaction between these two groups, and it will try to push the methyl not to here, rather go to the up. But there is also one problem is that when the methyl up, it start to see another steric interaction from the other side. Okay. So, you need to find out a balancing situation that this would be the minimum and that would be also the minimum. Under that scenario, that enolate you are looking for is going to be formed. Let us take a couple of examples and we see how it is going to be affected. For example, if I take the R is equal to an ethyl. So, R is equal to an ethyl group and I am making the E is to Z ratio I am looking for. So, I have the data. So, let me put that data, the value, what are the things. So, if you have a R is equal to ethyl, you get a 77 of E and Z is 23 percentage, and you put the R is equal to isopropyl, you get a 44 as to 56, and you put R is equal to tertiary butyl, you ratio become a 2 is to 98. So, you can easily figure it out that moment R is equal to ethyl, a moderate group. So, its group is staying majorly in the this position, and so we can generate the E inlet as a measure. Some portion is coming also the other side, so we get a 23% of the Z inlet. You make it a little bit bigger like isopropyl group. Now, this steric index is even more competing, so it push further more and you increase to the, now this is E is reduced and you increase the Z as a 56%. You increase even very bulkier like a tertiary butyl, no more this one is possible. So, it just everything come to that this stage and you get 2 to 98 of the E. Similarly, you can add couple of more like a, let us say if you add the phenyl, so you generate that is the 3 and actually the greater than 98 is also greater than 97%. Okay. So, we have understood that if we increase the bulky of the R group, we will shift from the E inlet to the Z inlet. Now, let me think about that this is R. Now, imagine that R is equal to an ester group, let us say OET. That means I am doing the reaction now with an inlet of ester, correct? Inlet of ester. So, exactly what happened at this position? So, at this position, what you have is you get this particular compound. Now, this R is this one. Okay. You can see which was previously ethyl group was directly connected. Now, it is via an oxygen connected. That means this interaction is not very significant. Previously was an sp3 carbon here and now is an oxygen which is only a substituent ethyl which is far away from this one. So, this interaction you have a not very significant. So, that means it will try to prefer majorly at the E configuration, correct. So, if you think about the R is equal to ethyl and so you can take a E is to Z ratio is coming 96 or 94 is to 6. Correct? You can take even further, let us say R is equal to an amide NET2. So, what you exactly happening now or you will have now, you will have this particular scenario and now we have an ethyl In this case, this steric hindrance is very high, okay, and so it will not going to be form at all. That means we will move, everything will shift to in this position. So that means in this case we will not have anything methyl here, everything move to the here and hydrogen will be here to minimize the interaction. So if that is the case, what you exactly get now from here, from this case you can simply think about that, you get a O minus and you generate a double bond here. So you generating a double bond where the methyl is in the right upside. So methyl and oxygen is the same side, and this is the amide and this is the hydrogen. So you will exclusively get at the Z enolate. So what we have understood that with the ketone, you have a sort of thinking how the nature of the R is there, and that governs which one is going to be formed. For the ester, very likely, mostly it will coming to the E enolate, but for the amide is very likely it will give to the majorly as a Z enolate. Okay. Now this is our enolate scenario where we can figure it out how we getting this in. Now let me take a close look that particularly this point R is equal to ethyl E72. Now maybe you think that for your reaction you need is R is equal to ethyl and you want to have a more amount of the E or Z enolate. So how you can do that? So this 23% whatever is coming is from this position, correct? Now if you don't want the 23%, you have one option to do that you increase the bulkiness of this one. You increase more bulky of the base. What it will do, it will push this one more. So majorly all of them will come to the other scenario. So one of the base for a bulky is that lithium TMP. Okay. So tetramethyl piperidine. This base. It is even bulkier than your LDA isopropyl base. So if you use lithium TMP for this particular case, okay, for this particular case, you can have E is to Z even very high. For example, that goes to now 86 is to 40. Okay, so significantly increases, but it's not enough. So you can even make a bigger that you add lithium TMP in combination of lithium bromide. If you use this bulky base, so that time it's become very exclusive. It become a 98 and this become a 2. So you could have an understanding that how we can play with the enolate geometry. Either we take care of the bulkiness of the R group, at the same time we have another control, the bulkiness of the base to adjust the steric hindrance in the formation state, and this is called, we call an Ireland model. Okay. So this is an Ireland model which follows a 6-member transition state where we can and figure it out which enolate is going to be formed majorly in this particular deprotonation strategy. Now the question is, there is one more thing we need to check it, that we can shift the selectivity from the E to Z using some additive. Okay. And that is HMPA, hexamethyl phosphoramide. Hexamethyl phosphoramide. How change is going to be happen? Same reaction you add in addition to that, like you have a lithium TMP. So, lithium TMP, lithium bromide combination. Along with that, you add HMPA, and that seems to be dramatically will change. For example, if you take R is equal to, we are looking for R is equal to ethyl. So, in case R is equal to ethyl and you have a E and Z ratio, now this is become 8:92. Reverse it, you can see that this combination have completely changed. This HMPA additive, which was previously 98:2, 98 for the preference of E enolate and 2 is the Z enolate, the same reaction, only additive of this one is reverse the reaction to come to the E as now very minor and the Z as a major. Now, what exactly happened that you add HMPA and game is changed? So, what is the role of that? This is coming from the Ireland model, or because of this closed 6-member transition state. But moment you add HMPA is highly coordinating. HMPA will coordinate with the lithium and it will open up, it will break this 6-member transition state. That means there is a no closed transition state and reaction will proceed through the open transition state. Okay. So, if I say this is a closed transition state and HMPA additive is actually making the open transition state. Now, how then is going to be happen? That means here Ireland model is not applicable and we are going to see how this is going to be happening for that particular. For example, the same substrate we can take for our reaction whatever we have had. Now, our condition is actually we are doing the same thing with the open transition state. Now, how is going to be open transition state? So, what is going to be happen in this particular case? I will try to draw it. Imagine that this particular carbonyl I am trying to draw, okay, and it has a, I will draw in the Newman projection. So, this particular carbonyl is this carbonyl, okay. In the Newman projection, the back carbon we cannot see and the other substitution we can see. So, the substituent, so this is the back carbon and so we have a 2 hydrogen here and 1 methyl we have. So, we can place that, but there is a condition, you must place one of the hydrogen perpendicular to the carbonyl functional group, thinking that pi star orbital is anti-periplanar to sigma bond. So, this CH sigma bond should be anti-periplanar to the bottom. Now, we have 2 other substituent, one is a methyl, one is hydrogen, you can put the both of them, one case methyl here, one case methyl here, or you have another option. Remember, this reaction still not happen. We are just showing how it's going to be happen. Clear? 2 possibilities will be there. Either you keep the hydrogen this side, a methyl this side, or you give a rotation, this methyl comes here, this hydrogen come this here. Now, between these two, will dictate which one is going to be formed or which one is going to lead the reaction. Very easily you can figure it out, and here is a lot of steric hindrance between these two. So, that is not going to be formed, and it is the one which is going to lead for the enolate formation. Now, if it is going to lead the enolate formation and you have a base and it is an open transition state, base is not connected to the carbonyl or not, a completely separate. So, you take this proton, and when the double bond is forming, you can see that your CO and methyl would be in the same side, and your hydrogen and this R should be in the same side. You understand, because the bond will be formed between this carbon and the backside carbon between these two double bonds, correct? So, if you see from here what bond we are going to be formed in that case. So, if I say it is that this bond is forming between, I would have a O minus and there would be a methyl, and from this side I have a R and here is a hydrogen, and this is going to be my Z enolate. Now, if it is comes from here, you can also see that this is going to be a bond and O minus. Now, the hydrogen is this side and the methyl is in this side, and I have an R here, and this is my E enolate. Now, if you look at that, why I was telling that if you add HMPA, you get the Z as a major product, and that is coming from here, because this is the reason. Once you add HMPA, you break down the Ireland model, you go to the via open transition state, and in the open transition state, you follow this two model, and between these two, this is much favorable over to the other one and leading to the Z enolate. But this is for the ketone. Remember, this is for the ketone. Same thing we can do also for the ester also. Okay. Now, if you look at that the scenario, what exactly I am trying to now draw it or write it, maybe a little bit scenario. So, what we are going to have now, we have that lithium TMP as a base and THF as a solvent, and we are going as a HMPA as an additive, and we have a E is to Z. We just figure it out, R is equal to ethyl. We have mentioned that it is 8 is to 92. Now, R is equal to OET, that means I am starting with an ester group, is also same thing, 15 is to 88. You can look at that. When you have a normal condition, it is the E is the major, but now we have the Z is the major. And now, if you look at the R is equal to NET2, then it is what you are expecting. It doesn't change. If you look at that, in the R is equal to ethyl, I supposed to get the Z enolate, and in HMPA condition, I thought to reverse it, but it is not the case. It is again the maintaining the same thing as it is. So, what is then exactly happening? Why the amide is not following the trend? Why the others are started to following the trend? That we can easily also figure it out from the from this particular scenario. But that is usually you can figure it out very easily that even though when you putting R is equal to NMe2 or other things, so between these two combinations, so one of the isomer is usually always getting the steric effect. So what we have is a steric effect around the system, and based on that we will predict what the things. So these are the few classical thinking that what we have for our reaction. Now what we need to have is that this one you understood actually, or you still have to have a problem with that. You see, moment you put is equal to N is equal to ethyl, you will really make the very strong interaction. So this is not going to be formed, it will remain here, which I was previously telling that this is going to be preferred when R is equal to ketone or ester, but the amide case is not the case, is always stays in this other side of this position. So that is what is going to be the case. Anyway, so now what we have is so we've somehow now got an idea that how the first step is happening. Now we will look for the two more enolates, how we can do that. So this is the lithium enolate. Similarly, we can make two more enolate. One is the silyl enol ether enolate. Silyl enol ether. Okay. So we can take the same example. How do we make? So if we take this substrate and we know how to get the E enolate. So this is the one lithium TMP, lithium bromide in THF minus 78 degree centigrade. So what usually you get? So in this particular condition you get a E enolate as a major product. So you get this particular compound, and then you react with the TMS chloride, that O lithium is now replaced to the OTMS. Okay. So this is an silyl ether, or we can say is an E silyl ether, and we also know now how to get the Z of that one. That means we will use the lithium TMP, lithium bromide, THF, and we add HMPA, same condition, and then we will lead to lithium plus, and when we quench this or react this intermediate with the TMS chloride, we can get the OTMS. So this is my E compound, and this is my Z compound. We will see how this kind of silyl ether is also going to be affected. One more enolate, that is the boron enolate. We would also like to know how these two is going to be happening. So you can take the same carbonyl compound. I am drawing slightly in this format, and there is a two hydrogen. One of them is methyl, one hydrogen is here. Is this drawing is clear to you? So this I just make that one. This is the way. Now, one of the reagent which is going to be used is N-butyl boron triplet, and the base is unique base diisopropyl ethylamine. It is in -78 degrees centigrade temperature and ether or THF as a solvent. What exactly happen when you add these two? So, this is going to be so what happened, this boron is a Lewis acid. It is first tied to coordinate with the oxygen center, and so most stable one is this one. Is the N-butyl group, or you can have a simply a minus and the oxygen plus, and triplet as a counter ion. What is that? Sorry, this methyl is not there. This is R, correct. So, now what we have, now the base is going to pick up. Again, which proton is supposed to pick up? As you remember in previously, the proton which is perpendicular to the carbonyl compound, which we have seen in the previous cases. So, this is the proton which is going to be picked up, and now if he is going to picked up, so you can imagine which boron enolate is going to be formed. So, I can draw that in this particular condition. So, this is the double bond is forming, and this is O B butyl whole 2 and a methyl and an hydrogen and the R group. So, that means I am getting a Z enolate. So, this is my Z boron enolate. Exclusively G boron. Particularly boron cases, we usually do not get any other E. If Z means it's always 98-99% selectivity. Now, I have one more condition which we will going to have, that the same reagent substrate. Now, I am going to use another reagent that is a slightly bulkier than this one, that is cyclohexyl. Means if I try to show you cyclohexyl 2, a boron, then chloride, correct. And the base I will use simply triethylamine, and in this case your reaction usually a little bit higher temperature at the 0 degree centigrade. What exactly happened between these two? This is a triplet counter ion, which is a non-coordinated counter ion, and this is a highly very strong Lewis acid, and N-butyl is a less bulky. Now, when you put the cyclohexyl, a bulkier one, what happened? It does not coordinate in this format, rather it coordinate because it will induce the more steric. So, it started to coordinate to this side. So, you have a now boron, one cyclohexyl group COI cyclohexyl and a chloride. You can have this format, because if you put in the other way, you started to have a bulkiness in that position, but now you induce another bulkiness here. That means you try to rotate along this line. So, if you try to rotate along this line, what you get? So you try to rotate along these lines such that this methyl comes this side and hydrogen goes to the other side. That is very obvious thought process. So I will do, I will have a R group, and then I will make the hydrogen goes here, a methyl goes here, another hydrogen come here, and then plus boron minus 1 cyclohexyl, 2 cyclohexyl, and the chloride. And at this point, your base has to pick up this proton. It cannot pick up this proton, as I mentioned, because this is the most weakest bond perpendicular to the sigma star of the oxygen. So if you have that, so now what you get? Now what you get in this particular case, that you make a double bond here, that become a O, B, and 2 cyclohexyl, and then I would have an R group here, a methyl group here, and an hydrogen, and so I would come to the my E. So E boron S, correct? So now we have a two condition: N-butyl boron triplet, which will lead to the Z boron enolet, a bulkier one, cyclohexyl dicyclohexyl boron chloride, which will lead to the Z enolet. So we have now three more enolet we already have. One with the lithium enolet, we know how to get the Z and how to get the E. We have now silyl enolither, that is also we know how to get E and Z, and now we have a boron enolet, we also know how to get E and Z. Okay. So this is the enolet part. The first part we have now understood that how it is going to be happen, and now we are going to the next step when this enolet is going to react with the aldehyde. So this is just initial part. We have now understood that. Any question from this part? Chlorine is missing. No, it is a boron has a three coordination. Once this minus comes, this chlorine has to leave. Okay. All right. So now we will move to the second part of the system. When the enolet is generated and how it is going to react with the system. So the reaction now we are going to study, let's take, we took an aldehyde, and this aldehyde is now going to react so this is my Z enolet, any of the enolet. Okay. Right now mostly the metal enolet like a boron enolet or lithium enolet. This is the Z configuration and a general reaction, and I took another aldehyde of a general aldehyde. Now we want to see which product is going to be formed from the Z. If you see your previously the notebook, that Z enolet is supposed to give you the syn product. Syn product. Now the question is, how do we now predict or how it is coming? So that we are going to see. So let's take that look at it, how is going to be happen. So let me draw the Z enolet first. So please follow me carefully. So metal or like lithium or boron, oxygen, carbon, this position I have a R1, and you see the R1 and R2 is the trans, or is the, so this is the R2. correct? This is the enolate. I would like to make a 6-member transition state in combination of the enolate. So, how I am pushing, I am just trying to draw that if I am going to have a 6-member, how it's supposed to look like, a chair like transition state. So, I am pressing the aldehyde at this position, okay, and then this is the your coordination of the metal or boron or whatever you are thinking, and this is the bond which is going to be formed enolate, and I have a substituent here, or and I have one more substituent here, hydrogen, correct? This is one. One more also option you have, that you make the R here and hydrogen in the, or R in the axial in the form, or hydrogen in the equatorial form. So, you can draw that one as well. So, let us imagine that. So, I have a same scenario, oxygen metal that goes to the bond forming, oxygen coordinating. I have an R1, a Z enolate, R2, and now I have an R and in hydrogen here, and this is the bond which is going to be formed, correct? So, you tell me which one is going to be really formed. You look for that in the 6-member form, and you can imagine that there is a strong interaction between these two, because this is a diaxial interaction between these two, and in this case you will also have an interaction, but it's a gauge interaction between these two. So, that is between these two, this is going to be win slightly. So, what product then you get? So, let me put the bond formation. So, this one coming back, the enolate comes back, this pi bond reacts to the carbonyl center, and then this is picking the metal, and which will be, when you add the water at the end, you become a OH. Now, first hand, let us just we draw where the bonds are breaking and bonds are forming, okay. So, I will just draw again the same thing. So, this is the what is going to be happen. I can see that there is a, this become a carbonyl and this become a R1, and there is an R2. If you want, I can put an hydrogen here for our understanding that there is one hydrogen here. Now, this is a new bond which is formed. From that bond, 3 other bond is there. So, one is going up, one is going that, and one is going this format. This is the R. This become a OH, and this is already the H. This is going to be formed, okay. Now, this compound I want to draw in a linear form, and that is very, you need to be very careful. For example, in a zigzag form, okay. In the zigzag form, you can start from one side. So, you go up, you go down, you go up, you go down, you go up, you go down, or in the right side, you go up, down happen. And at this position, you can have a substituent. So, if substitution in the beta form, that means it is facing you, or if there is substitution in the alpha form, it is away from you, correct? Now, I would like to draw this compound in this format, because most of the book you will not see this one, you will see directly this format they have written. So, we have to know how it should be looking. So our first job is to find out where is our zigzag. So follow my line. So I am going from here, or I am going up, I'm coming down, I'm going up, and then I'm coming down. So I found my zigzag, how it's supposed to be, and zigzag is starting from my right hand side. Yeah? This is my left hand side, this is my right hand side. That means I will start my zigzag from R, and from the R I supposed to go up. When I go up, I see a substituent, hydrogen and OH. Hydrogen and OH. Hydrogen is in the beta and OH in the alpha, correct? So I will put that OH at the position like that. This is the axial and this is the equatorial position or in the line of the position. So this will be the beta and this will be the alpha. From this position, now I should come down. When I come down, I come to here. When I come here, I see a R2 substituent. R2 should be alpha or beta? Beta, why? Because it's downside, no? Why are you saying beta? It should be alpha. So I put the alpha down. Now from that, I supposed to go up. I supposed to go up and I see a carbonyl and the CO, that is as such R1. So you can see now what is exactly happening. If I try to give a number 1, 2, 3, so 2, 3, I have a scene selectivity. 2, 3 scene selectivity. As I said you, if you look at your notebook previous page, that if you start with the Z enolate, in principle you are supposed to get at the scene selectivity, or it should be a scene product. Okay. Now I said two product is forming, this one and the mirror image of this one. You look at your page, next page. So in the mirror image means these two are the beta. How do I get the beta? What you can do, right now I have a, look at my hand, this is my enolate and I bring the aldehyde here, okay. But there is a possibility also you bring the aldehyde in the other side also. So that we can also look at it. So if you look at the aldehyde in the other side, for example, now how do I see that? So you can have an, you can simply try to draw a 6-member ring, and our goal is to make the aldehyde in the back side, and then I would have a enolate, and that is the Z enolate, and we should have an oxygen, that should be the scenario, and that is the metal which is connected to this one, and this is the new bond which is going to be formed, and this is the coordination of this one. We have the RO, I think we are using RO1, R2, no? We are using R1 and R2. So this, now if you draw this one, same thing we will follow. Please have a little bit practice later on, because you need to understand how this 3D goes to the 2D format when it comes to the zigzag. So best idea is initially don't change anything. First connect the bond which is forming, and then you will see what is exactly going to be happening. So I make this bond I formed. I have an hydroxy group supposed to be here. There is an hydrogen in the aldehyde. This aldehyde, this R. There is an R2 and a hydrogen. I can keep it if I necessary. And then this become a carbonyl, and this become a R1. See whether you have able to follow it. What I did, not much thing. So this bond form, this react, and this becomes a OH at the end. And again, you try to find out, because I want to now draw in a zigzag format, and you need to figure it out, where is your zigzag. Okay? So you can very easily figure it out. I can start from this one, I go up, I come down, I go up, and then I will change it. So now my zigzag start from the left hand side, where we are going to the R, and from R I am going up. When I go up, I have a two substrate, H is axial and this is the downside. So OH is the downside of the OH. Now I come down, I come to here, here I see R2 is also downside. I go up and the carbonyl and then R1. Now these two you can see I just flip. Flip means out of the planes flip, because that if you want to compare between these two, this carbonyl is in the right side and R is in the left side, but there carbonyl is in the left side and the R is in the right side. Let's flip it and see. So if you this molecule is there, you turn over. So what exactly going to be happen if you do that? So I will start with the, so you will see that, so when it goes to that side, R comes here and the OH become a beta, and then R2 also become a beta for this one. So you can see that now R1, R2, R1, R2, these two are the syn, these two also the syn, but this syn both are in the beta and in this syn both are in alpha. Then relationship between these two are the their enantiomer, because so far we are only dealing with the racemic reaction. So these two is going to form, but the relative stereochemistry. So relative stereochemistry would be the maintained in both the cases. This is also syn, this is also syn. But in this syn, we have a 2 are in the beta, in the other syn, 2 are in alpha position. So this is what is the syn select. Okay, so we can take a break.
SwayamPrabha, Digital India, Educated India.